This will be a simulated operation of a centrifugal compressor using the AirLogix controller. We will step through starting, loading, exercising all 4 PID loops, unloading and stopping. For this lesson, we will be focusing on 5 primary variables: the inlet valve, motor current, the bypass valve, machine pressure, and system pressure. Before starting the compressor, all start permissives must be satisfied. For example, if oil pressure were lower than the start permissive value, an alert would display in the message center to tell you so. In this case, the oil pressure start permissive is set at 10 psi, and is unmet. Once all limiting conditions are satisfied, the message display will read, "Ready to start." Notice that system pressure, or the header pressure, is currently about 75 pounds. But machine discharge pressure and motor current are both at 0. This is an obvious indication that the compressor is not currently running. For this demo, I'm going to use a graphic that represents a typical centrifugal compressor. I'll click the Start button, and you'll see motor current jump rapidly as the motor begins turning the compressor arrow end. In real conditions, the motor inrush current will cause this variable to briefly peg at full value, before returning to normal running amps. Next, atmospheric air is drawn through the inlet filters, past the inlet air temperature RTD, and to the inlet valve, or in some cases inlet guide vanes. The inlet valve is used to modulate the volume of air into the arrow end of the compressor, and to meet the current demand of the process. At the discharge of the compressor, air pressure is measured. This is sometimes called machine pressure and should not be confused with system pressure. When the compressor is first started, the bypass valve is open, and any air passing through the machine is exhausted to atmosphere. Because discharge pressure is less than the current system pressure, the check valve prevents any backflow from the header, and this compressor currently contributes nothing to the process. I'll click the Load button, and we'll watch as the inlet valve begins modulating open. Notice, the inlet valve says it is controlling to DTL, and once we're at DTL, the bypass valve begins controlling to system pressure, and modulating closed. Now you see discharge, or machine pressure, climbing. Once machine pressure exceeds the system pressure, the check valve will open, and we are actively contributing to the header. Now, the bypass valve is completely closed and there is no more blow-off. And for the moment, the inlet valve is controlling to FLA, trying to load the compressor into the system as quickly and safely as possible. In the interest of time, I have increased the speed of this process of loading the compressor into the system. Now try and keep an eye on 2 things. On the AirLogix screen, watch system pressure, as it approaches the pressure set point of 99 psi. At the same time, watch the inlet valve. Once we reach the pressure set point, the valve will begin controlling to a system pressure PID and modulate, to keep a constant pressure. Now the compressor is fully loaded, the bypass valve is completely closed, and we are controlling to the desired pressure set point. Now let's see what happens when the process demand for compressed air begins to decrease. As pressure and flow are inversely proportional, a reduction in flow means an increase in pressure. The result is, the inlet valve pressure PID will begin to modulate the inlet valve in the closed direction to reduce the pressure back to the set point. In this example, the motor current has reached DTL, and the inlet valve is now controlled by the PID loop for DTL. Were demand to take the compressor below DTL, and this were the only compressor online, it would be necessary to modulate the bypass valve to prevent the compressor from surging. You can see that here. In this case, only some of the work performed by the motor to compress air is being used by the process. Some portion of it is wasted in blow-off. AirLogix will always work to minimize or eliminate this condition. This is particularly true when more than one compressor is used and an air master load sharing is applied. We'll cover that strategy in a future video. Now, one last thing I want to show you before we stop the compressor. The motor current indicator in the lower center section of the screen is at the lower end of the green range of the compressor performance gauge. Once again, we call this DTL. It's a variable for minimum throttle that is calculated using air density. That minimum throttle point is dynamic. When the inlet air temperature becomes cooler, and the air becomes more dense, the DTL variable reduces, allowing further turn down of the compressor, before the need to open the bypass valve. Watch the DTL number as it floats between 128 and 123 amps, further improving the efficient turndown of the compressor. Notice how actual motor amps follows the DTL lower, and that the result of this is the bypass valve closing. Now, as demand has once again increased and the inlet valve is modulating to pressure, I'm going to wrap this session up and unload the compressor. AirLogix will prompt you to confirm the command to unload, in order to prevent accidental unloading that could impact your process. Now the bypass valve is open, the inlet valve is closing, motor current is dropping, and system pressure is falling. At this time I'm going to press the stop button and answer the confirmation to stop prompt. And you see in the message center, a coast down timer begins. This allows the compressor time to coast to a stop before allowing another start. Once the timer is complete, and provided all other start permissives are met, including the limit on starts per hour, the message center indicates this compressor is again ready to start. This completes this demonstration of the AirLogix centrifugal compressor controller. Watch for future videos on load sharing and other solutions. And thanks for watching.